Okay, let's do the last little piece here, which will be kind of a discussion piece, administrative stuff too. For those of you who've been hanging on, wishing for administration, always the best part of class. So administratively, a couple things. One, um, because of TA demand, we are just moving all questions to Piazza. So this means we are retiring 537 help. Our stalwart of helping people over the years now is dead. Um, Sending mail to that will not get a response other than please use Piazza or no response. The reasons for that is that the TAs like responding on Piazza, and the TAs like waiting for me to respond on this. And you can imagine I don't like that. Um, and the great thing about Piazza, though, is also tracks all these statistics, so I can yell at the TAs when some of them aren't answering enough questions. So this is good for you. Um, it's good for me. It's bad for the TAs. But that's okay. We ignore the TAs for now. So use Piazza to ask questions. I've put that on every future project's description will say exactly that. Now, I'm getting more and more questions about things like, I don't know, these concepts that you all are concerned with, like quote-unquote grades and other things that related to that. So I thought I would talk about that for now. Grades. Um, Everybody gets an A. No, that's not how grades work. Um, it could happen. Hasn't yet happened. So what I'm working on but haven't finished is just a summary of where you are so far. Summary. So this is coming, and what the summary will say is like, here are your scores on P1A through whatever P2B, and then it'll say kind of approximately what this looks like in terms of a letter grade. Like for example, F. Um, no, you shouldn't have that. That's mean. Like for example, A or B or whatever. So I'll just give you a sense of that. Just informally, what I really want out of class for you is for you to um, learn what we're talking about. That is measured on exams. So there's no magic there. You take the exams. If you do well on them, then I know that you've understood what we're talking about here in lecture. That's half the class. The other half of the class is the doing, the projects. And what I value there really a lot is that you did some or most of, or all, hopefully, of the projects. Now, if you're not getting a perfect score, but you're getting, 80% on some of the tests or whatever, that's 100%, that's fine, right? That's going to still be a fine grade. It may not be that everybody who gets most of the credit gets an A, but it's certainly not like a bad grade. It means that you've put an effort, you've understood most of the project, and yeah, maybe you didn't get all the corner cases to work. So if you're doing that, you certainly don't have anything to worry about, unless, of course, you completely fail the exams, then you'll have something to worry about. But we'll worry about exams shortly enough. So if you're doing that, it's going fine. What I do get worried about or more unhappy with, if I get unhappy with anything, is just when there's no, when you don't turn in a project. That's a bigger problem. And so I'll say that in this summary. I'll really try to get this done soon. There's still some grading that needs to be done, of course, for that to finish. And then we can talk about things more if you're having a problem with that. So that's coming. When will that be done? Hopefully soon. We'll find out. There's also we're finally doing the contests. Those should be for, what was it, 1A and for 2A, yes? And so these are going to be done soon. They basically all the scripts are written, etc. And so we're just coming up with the final winners. We will then have a Oscar-like ceremony. I will expect everyone to dress in their finest Oscar tuxedos or whatever evening wear. We'll have a big award. It'll be a big deal. The press will be here. So wear your best, and we'll do the contest winners soon enough. And the Oscar and the T-shirt goes to. There's no winners or losers anymore on the Oscars. It's just the Oscar goes to. So it will be the T-shirt goes to, and then we'll call a name. It'll be very dramatic, and of course that person won't be here. And so in absence, someone else will have to come up and accept the T-shirt for them. So that's that. That's coming up soon. T-shirts, yeah, etc. And that's going to be very exciting. And we'll do a couple more of those as the class goes, as we'll see shortly. So that's grades. That's contests. One more thing before I get to your question. Coming up is the exam. We'll do more on this next week. Until now, you should be not super focused on this. Next week, depending on how much you're getting, what's going on, you should start thinking about this. And then the week after, you should definitely think about it, for example, by showing up at the exam. So that'll be the following week. And then we have the beauty of this arrangement of how we're doing things is you will take the exam, and then you will have this blissful time of your life, which is called spring break, but it's actually a real OS break. There will not be a project hanging over your head. Yes, let's clap for that. The best news you've had. If somebody is ruining your spring break, it's not me. It's somebody else. So direct your ire, your rioting, your thumbs down during class at those people, but not here. We will have a true spring break here, which is good because I want to be on spring break too. So that'll be great. Okay, there was a question. The bar got high for applause. It's like no work over spring break. That's true. That's true. That's a good point. I shouldn't have done that.
Previous project,
yeah.
Like a perfect score on the test that we were given didn't necessarily translate to a perfect score.
Yeah, but it's close. It should be close to a perfect score. Right. So just to be clear on that, occasionally we'll add maybe a test, but not many after you've turned it in, which means you might miss one test because you didn't do something right, honestly. So I guess that's what we call it, doing it wrong. But you'll be able to look at that test and complain about it if you don't agree with the scoring. So this is going to raise a lot of questions. I can see. You have
get to learn about what those extra tests.
Yeah. The TA will share the details of the test with you. Yeah.
And the same thing goes with the contest, phone contest. What we get to learn about. How they
right, to some extent, to the extent that it doesn't give away some next project of ours. Yes, we'll talk a little bit about how the contest winners did their magic, but we won't talk about it a lot. And then there were some other requests too for talking about some old projects, and we'll do that a little bit maybe today. Yeah. That's a good question. What is the semantic of a late day? You're like, actually, it was my partner's late day. It does seem to imply you get 6 late days instead of 3. Does that seem too generous? I heard one yes in there. So I'm thinking yes. I guess, So here's the concern. Let's pretend we're both adults when we all know really only I'm an adult. So you're in school, they're not adults, but some of you are adults. But in any case, in this adult conversation, the concern is that people will be like, oh, I have so many late days that then I will not do this one for a while, and then it'll bleed into the next one, and then suddenly you won't get either of them done. So that's what we're trying to prevent you from hurting yourself, right? So don't abuse it, but it does seem like because you could use a late day on a project partner time, you could come into it unevenly. So that's weird. So it seems like you could get up to 6 by that accounting. Don't stretch that. Don't use all those days. Use them wisely. But I guess what is the semantic of a late day with partners? Basically you should be like, oh, I took an extra day, maybe 2 days for a single project. If you're going beyond that, you're probably going to start bleeding into something else, and that's going to be a problem. So don't do that. Yeah, so P3, P4, P5, P6, P7, P8. Any future P projects will be done as pairs or by yourself. I mean, we're not forcing you to do a pair if you don't like human beings and stuff like that. So yes, yeah. Oh, right. So yeah, so the question is, since there's an actual late policy, when does that when does the clock start ticking? I kind of consider, like, if you're up late and then you stay up late and then you get it done at 4 a.m., that's kind of like your free late half day or whatever. So that's free. And then really turning in the next night is when you get charged. So yeah, you can still get that freebie if that's what someone already asked about that. Yeah. Yeah. You're like, I should just shut people down at 1. How to make friends in class. People can always log in remotely is the problem. So you should be able to go home and finish your project, right? So that. Sorry? Engineering hall doesn't close. Perfect. Yeah, why are we clapping for that? Some engineers in the room, perhaps? We are so far beyond wanting to be in class, I can tell. They're like, if we just filibuster the rest of class with our questions, we don't have to learn this thing. Okay, yes. But you need a card or idea to enter engineering. Boo! Okay. Let's ask questions that I can answer. Okay, what else? There was another question. Is it about engineering? I'm not answering it. Yes, don't take. Basically, what I'd rather do is just you turn in the projects when you finish them. But I can't. It doesn't quite work. So we have a slight policy around it. Don't abuse it. Okay.
Would you is paired programming recommended?
It's not paired programming. It's like you have a partner, so you can work with them however way you want. The best way, of course, is to sit next to each other and have one of you doing something, the other helping, and then switch around a lot. What you're going to end up doing, some of you, is like, you take that half, I'll take this half. See you in 2 weeks. And then the problem with that is you don't learn half the stuff. So don't do that. But you have to kind of figure out. Yes, I would recommend having 2 people because it's just more fun, right? Unless your partner sucks, and then it's really terrible. So, the other thing is, if you don't have a partner and you want one and you don't want to use Piazza to get one, because I think there will be a way through there, is just hang around after class at the front, okay? Hang around, don't look, weird, just look normal, look like you know what you're doing, be furiously scribbling something, look attentive, and then, eye contact, and, go from there. So find a partner at the front of class or through Piazza because you don't like human contact. Okay, any other questions? That was way too much of a diversion, so we're not going to do this as long as I might like, but that's okay. Anything else? Why am I recording all this? People will be like, there's going to be someone at the university that eventually is like, this is how you run this class? Yes, this is how we run this class. They're like, are the students learning anything? I don't know. The answer is maybe. Okay, here is our wonderful 1990s web page, and what we can see here is P3 is linked on here, and we can click on it, and we can see here is the use Piazza, so don't use 537 help anymore because we won't answer those questions. This is due by Monday 3/19, late, so whatever. And then there's 2 parts to this, so all of them will have both the Linux. We've done this very gentle introduction. So gentle introduction, doing one at a time, so you just focus on the one. Now you get partners, but you also have 2 due. These are still a pretty gentle projects, I would say. And then you take the exam, which of course will be terrible. And then you'll have spring break where you'll think about the exam and how terribly that went. Then you'll get your grades back on the exam. You'll be like, that's going terribly. I hope P4 goes well. And just warning you, P4 is going to be absolutely the worst project of the semester. It just has to be that way. I'm not saying what it is. I'm just saying it's going to be bad and you're not going to like it. And then if you get through that, you're going to be like, this class is awesome. And if you don't, you're going to not say that. So just preparing you for the future. This is going to get worse than this one. So this one is going to be a little bit fun. Remember our old pal Zip? Zip was a simple program which did a compression. Now we're going to do a parallel zip with p threads. So let me just run through that a little bit with you. And we won't spend a long time on this. And then the XV6 side, I'll spend a little more time because there's a little detail there that you'll want to know. So pzip is pretty easy to understand. You create a bunch of threads, and you try to make the zip run as fast as possible in parallel. Okay, so you have to, given a file, you have to kind of have threads each zipping a part of it at the same time, and then somehow combine all those results and write the output, which is the compressed output. Does the basic idea make sense? Do people remember zip? I guess I should have asked. Remember our friend zip? We do a run length encoding where we turn runs into like, oh, there's 12, the letter C, and then there's 300, the letter, D or whatever. So if you don't remember that, read the old zip description. And then these are just some things you should think about when you're building the zip. The first, of course, question is how to parallelize the compression. That's kind of the central challenge. How to split up the work across a bunch of threads. So hopefully that'll be fun to think about. This is not required for like a good implementation, but is required for what we would call a best implementation, which is basically if some thread, let's say you have two threads and they're each zipping, let's say let's say one file, two threads, each are zipping half of the file. And let's say one for some reason is running a lot more slowly, then you'll have a problem, right? Because you've given out the work half to one thread, half to another, and the one's running a lot more slowly, so you run at the rate of the slowest thread. So what a good program will do is essentially chop work into somewhat smaller units, and then hand them out to threads as they run. And then if there's a slow thread, it's okay because it wasn't given that much work, and the other threads will get more work. That's a good implementation. A fine implementation will just divide up the work evenly and hope that no thread runs more slowly than another. So that's that. You have to determine how many threads to create. There's some calls in Linux you can make in order to find out how many CPUs there are. You can imagine that would be relevant to how many threads you should create. What's also relevant, and we can talk more about this in coming weeks too, and maybe the TAs will talk about this more, is just parallelizing something but then doing the parallel work very inefficiently makes for a slow running program, right? Speeding up a slow program and making it slightly less slow with threads isn't that great of a thing. So you should think about how to be efficient within your single thread performance too, and we'll talk more about that. We'll probably give some more hints around that in the coming days. And then one specific related point there is how to access the input file or files efficiently. And so what we're suggesting there is instead of calling fread or read, or certainly not fgetc or anything like that, you should open the file and call mmap. Mmap is a memory mapping interface to files. What that allows you to do, and you can read the man page to learn more about this, is it allows you to basically map the file, the input file, into your address space, and then just use pointers to go through it. You can imagine each thread giving a pointer to a different part of the file and then processing that in some way. So use mmap. That'll be a very efficient input for the reading of the file. The grading is down here. First, we'll just kind of run all the old correctness tests. So your zip has to work. Having a fast, incorrect zip is not a good outcome here. And then we'll test, we'll basically give you some performance ranges where, full credit will be faster than, X, most of the credit will be, whatever, and so forth. So we'll just give a few ranges of performance, which you'll be able to test on your own. Yeah. Yeah, so we'll give a standard machine, and we'll say if you run it on here, this is what roughly you should expect. Now, it's always a little bit hard to tell because there'll be a bunch of people running and things like that. So if you're sharing the machine with somebody, your benchmark timings won't be exact, but you should have a rough idea of where we should go, and we'll be a little bit loose on those. Yeah. And yeah, I think that's a natural contest, is to make the fastest parallel zip. In fact, that's I haven't told you yet, but the TAs wrote the fastest zip for the previous one because they used threads. So they cheated. You didn't know how to use threads. So yeah, there will be a contest with this one too. And I'll put that on the webpage. I didn't put it on there. Other questions? The basic idea, pretty straightforward, but getting all the details right should be hopefully some fun. So bringing back our pal zip as a gentle intro to threads in Linux. Yes? Yeah, so we reserve the right to test them elsewhere, but you should be using these interfaces to find out how many processors there are, and you should use that in your code. So if we somehow ran on a machine that had 16 cores or 32 cores or 128 cores, your program shouldn't just use 4 cores. That would be a bad implementation. Yeah. Yeah, you. Can you use the GPU? Assuming there's a GPU, yeah, I guess so, but it should run on a machine without a GPU. So you need to have a way of testing, is there a GPU, and then using the GPU in that case. I don't think, do the lab machines have, they might actually. Yeah. Yeah, I mean, if you want to, it's nothing we're going to help you with, so if you're causing problems, like, don't ask questions about it. But that'll be enough to make everyone else feel uncomfortable, so thanks for that question. Everyone's like, what, I have to do that too? No, you don't have to do that. But if you, maybe that's a contest winner. Yeah, there's always so much to know. That's the disappointing thing about the world, I guess. But so be it. Okay, so fun little project. Shouldn't be too bad, and making it fast might be fun. So now let's talk a little bit about the XV6 side, and then we'll be out of here. So we won't spend, like I said, we're trying to get done early, so we'll probably get done in 15 minutes or so. Let's just understand the XV6 project, and then we'll just take a peek at some code that you might be interested in. So this is the XV6. On the Linux side, we're just kind of going ahead into the concurrency part of the projects. Projects always lag lectures somewhat, right? Because you have to kind of learn about it here before you go and write it there. But they lag at different rates for different reasons. So on the XV6 side, we're still in the virtual memory part of the course, so it's lagging a little further. On the Linux side, we're going ahead into concurrency. So that's just life. This XV6 project has 2 parts. One is to implement basically a nice debugging thing, which we are used to in all the systems today, which is a null pointer dereference. We're going to make that work like we would think. Normally when you have a null pointer dereference, the system says segfault, and you're like, oh, that's a problem. And then, you put something on Piazza, my code segfaulted. So don't do that. Actually debug the program, find where the problem is. But on XV6 that doesn't happen. So let's make sure that that's true. So let's say we tar whatever, this, and then where is it, TA, something like that. Okay, so let's do that. And then let's not make it yet. Let's go ahead and make a user program. Oh, sorry. There we go. So let's go ahead and make a user program, which is going to be our null pointer dereference program. This is not a program I recommend writing in general, except for this project. Let's start with the ls program because we know that works, and let's just get rid of most of it. And then let's not do the ls program. Let's do something else. So let's say we have a pointer to a character, and then let's say it equals null. 0 is just null in C. And then we know that we have of course, if we we set a pointer to null, and then we print its value, for example, something like this. Then, well, this is not a good thing to do, right? Something like that. We dereference this null pointer, deref null pointer, and that's bad. Deref null, bad, right? And when we run this on Linux, we know the program will segfault. It's actually undefined behavior, but the common case is it will segfault. So let's see what happens on XV6. Let's see if I did that correctly. Okay. And go ahead and run our program null. Prints out something. That's great, so that's not too useful. So let's go ahead and change the program a little bit. Let's print it out as an integer. Back an unsigned int. So you can see a bunch of stuff that doesn't look that relevant, and then we can actually see the character part that we got, which was D8D. So let's see if we can figure out where that is. Well, if we use our old friend objdump, and yes, nobody refers to their old friend objdump that way, but we will in this class because we're in the OS class again. And let's go ahead and look at, well, let's look at null.o. It's fine. And what you can see is loaded at what it thinks is virtual address 0 when it's making this program is it's going to, the very first part of this very first instruction is in fact the bytes 8D. And so 8D is just the first byte of the first instruction. So when instead of getting a problem, we get, here's you're reading through your instructions. That's what happens in XV6. So what your project is going to be is remedying that and making this actually fault. Okay? And the way you're going to make that fault is by not loading the code at 0, but rather loading it, say, at 4K and above. And then when making that the 0th entry in the page table should be, say, that this is an invalid page and therefore cause a fault when you access it, like it would happen in Linux. Hopefully that idea makes sense because you remember something about what we learned with virtual memory and all of that. So now what I'm just going to do really quickly is point you to a few spots in the code where you're going to be staring at. Like all XV6 projects, it's stare, 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 do something, it breaks, it panics, stare some more, write the 5 lines of code, then it works. Then you scream, hallelujah, and then you're done. So let's look at where we're going to add that code. So we're going to look in the kernel, and we're going to look first in probably the most important place, like where a program gets loaded into memory, like a new program like null when we run it from the shell. And what system call is enacted when we are loading a new program into an address space? Exec, yes, we remember from the shell that we loved so dearly just recently, that exec is our friend there. So let's go ahead and look at exec.c. And right at the beginning of exec, so what exec has to do, remember, often like in the shell, we've called for, now we have a newly running child process. That child process is going to call exec, and then it's going to run, it's going to load a new program. It's going to load a new program into memory, and then it's going to essentially return into the main of that instead of continuing as the child, which is a copy of the shell. So that means it has to read from the disk the binary. All these binary executables are in this format called ELF, which is just one of many formats that people have created for binary executables. You don't have to really understand the details of how ELF works. You could, if you're like, a crazy person who likes to understand every detail of everything. That's totally fine. You should go read about ELF. There's a lot to read about. But basically, this code already knows how to read through an ELF like binary and load the relevant pieces of text and other things into the address space and then start executing it. So here's where it actually says right here, load program into memory. And so this is a cool little loop that you're going to spend some time understanding. And what it does is it reads in a little bit of header information, and then importantly, it calls these two routines, alloc UVM, user VM space, and then load UVM. And so the allocation piece is basically getting the page table ready for all these pages you're about to read in and marking them valid. And then the load UVM piece is then reading the pieces from disk into memory, and the page table piece is pointing at those pages. So you're going to have to understand how these might change, because right now it's loading the code at address 0. It's starting at 0 and loading up from there up to whatever size. In fact, we could go ahead and kind of print that out here. You can see we start at size equals 0 here, and you can see, in fact, we're using this virtual address that's coming out of the ELF executable. We're using that in order to figure out what's going on. So let's go ahead and just print out those things, like the VA that things are getting loaded at, and then, like for example, the like the size of the thing that is getting loaded too. So let's go ahead and print out size %d or something like that, and then let's go ahead and do ph.va and then ph.file size or something like that. Let's see if that builds, and then let's go ahead and run it. And you can see immediately that a couple processes have already run, and then when we run something else like ls, we can see that ls also prints out some information, which is saying it's getting loaded at virtual address 0 and that its size is of this certain size. And each program, of course, has a different size when it's running. It's like the shell or init or whatever. So in this loop, you're going to have to figure out how to change this loop a little bit so that things don't get loaded at 0, but they get loaded at somewhere else in the address space, 4K and up. And that will make it, the nice thing about that, you don't actually have to, all the other pages that haven't been loaded, haven't been made accessible, those will fault whenever you access them. So that part, you don't have to change anything. You just have to kind of load things correctly. So that's one thing to look at. You'll have to understand this code here in a little more detail. And of course, to understand that, you should probably like read through vm.c and look for alloc uvm and kind of make sense of what it's doing. It's messing around with some page tables and stuff like that, and load uvm. Right, so these are all pieces of code you're going to have to look through a little bit. We'll talk more about them in a second. Kind of just a cool point here, at the end of exec, there's this little bit of code here. What is this code doing? Anybody guess? What is exec doing? So it's loaded a bunch of code into the address space and some static data. It's then, which it makes sense, right? You want to load your code into the address space. What is it doing with this? I guess it says some stuff here. So who can read this comment? What is it doing? It's initializing what? Stack, right? Where does a stack get initialized? Well, somewhere in exec, the stack is going to get initialized because you're about to call into main. Main expects argc and all of argv to be on the stack. So this is where that happens. It's happening in exec, and it's getting loaded right here. And you can kind of look at this code in some detail if you want to figure that out. There's this last kind of little interesting piece, which is what's on a stack. What happens when you return from any function in like x86 or C? What's happening when you return from a function? How do you know where to return from, or where to return to? Sorry. You pop it off the stack, you pop a return address off the stack, and then you, essentially the return address, the return instruction jumps to that, whatever that popped address is. So that means even when you're creating a proper stack, you would put a return address on it. Here they put FFFFF, FFFFFF, which is they say it's a fake return PC because they want to generate a problem if you return from main. And if you ever notice this, if you don't put an exit in one of your, like you're writing a little user program in xv6, has anybody ever done that by accident? And then what you see happens is when you run that program, is it says, oh, there's a trap. Because what happened is you basically return to an address that you shouldn't be able to access. It's not mapped into your address space. And in fact, it tells you what the instruction pointer is at that point. It's FFFFFF. It jumped to an address that was a bad address, which causes a trap to be caught by the OS, and then the process dies in this inglorious way. So, so that's where that comes from, and that's why xv6 basically requires you to call exit to not get that to happen. Of course, it's not that terrible when it happens. It just looks like something's horribly wrong. If you wanted main to return properly, what you would do is you would have kind of a wrapper function that gets called first that calls main, and then when you return from main to that wrapper function, it would properly call exit all the time, so you don't have to add exit to your code. So that's exec, and you can see that's more or less most of what happens. There's a couple other details there, and then it returns. So study exec. There's also, you should look at, you're going to have to look at fork a little bit, because fork of course, creates a copy of an address space. And so you have to think about what happens when an address space gets copied, because now you're changing something about the address space. So it'll be a little bit of work understanding that. And then kind of the last place to look is on the user side, in the makefile. There are a couple pieces here that are worth understanding. Every user program is now compiled, and it says what the entry point is called. It says it's called main. That's not going to change. But it says what address the program will be loaded at. That's actually part of the compilation process. Here it says it's 0. When you're doing this, it can no longer be 0 because you don't want it to be loaded at 0. You want it to be, the program to be compiled as if it's loaded at, say, 4K or at hex 1000. So you'll have to change this line too in the user makefile. It'll be hard to find without assistance, so that's why we're just pointing it out here. So that's part 1 of the XV6 project, staring at exec and to some extent fork and a little bit the makefile, and seeing if you can kind of relocate everything so that that first page isn't a mapped part of the address space. So that's kind of I would say the slightly harder part. Then the other piece that you're trying to do is right now code in XV6 is not just read-only, it's read-write. It's kind of a laziness on their part. So what you're adding is a ability to call mprotect, which given a pointer, a virtual address and a length, will basically make a page or a number of pages in your address space read-only so that somebody can't write to it. And then munprotect undoes that and makes them writable again. So you're adding 2 system calls, and they're just going to change the protection bits inside of your address space of the running process. So a little bit of details there, but that's the basic idea. Where do you have to look for that? Well, again, you're going to end up looking in VM, because in VM.c you'll see a bunch of examples where code does things like gets a page table entry, by calling this walk pagedir routine. And once you have a page table entry, you can start messing with it and, for example, changing the protections of the page from read-write to just say read-only. So that's going to be a little work. Neither of them require that much work, but they do require some understanding. So stare at the code, try to make some progress. And in all of these projects, what you should absolutely do is do the minimal step at a time. Don't say, I figured it out, and then write all the code and then run the tests. Instead, do the minimal possible thing and see if you can make one step forward, like printing out values to say, are these values what I expect them to be? And then slowly try to change them and go from there. So always work incrementally. Okay, so that is plenty for now. We'll talk more about this, of course, in the future. So good luck.